Hello everyone, my name is Purnima Padmanabhan and I'm an assistant professor at RIT, and welcome to my talk on thermodynamic mixing rules for block random copolymers. Uh, this group was a collaboration between my group and Brian's group at Auburn University, and so we did a lot of the simulations and Brian did, and his group did a lot of the experiments, and some of the data are also from the work he has done with his postdoc, former advisor. So most of us are familiar with the block copolymer phase diagram. And so here, by changing the composition of the AB block copolymer, you can get several different morphologies. So the center, when you have 50-50 composition, you can get the lamellar phase. And as you go left or right in the phase diagram, you can get different phases. You can go from lamellar to gyroid to cylinders to spherical micelles. And the y-axis, you have Flory-Huggins parameter times the degree of polymerization. And so Flory-Huggins parameter is dependent on temperature and the chemistry that's chosen. So in this phase diagram, the location of the order-disorder transition at equal composition has been found, and it's equal to 10.5. So here again, with this phase diagram, you can change the morphology using composition. But once you pick a chemistry, you have pretty much fixed the chi value, and then so that also fixes the ODT. So the only way to change ODT is by changing N once you've fixed a chemistry. And so we are interested in block copolymer phase behavior because they can be used for lithography applications. And so really having a tunable domain size and having an independent control of the ODT is really desirable. But it's not possible with simply a block copolymer. And so the idea that people have is you can have a block random copolymer, where you have one block that contains a monomer of a single type, but the second block contains monomers of two types, again distributed randomly, and you can change the composition of the random block. So now that you have these two blocks, you can now define an effective Flory-Huggins parameter, and that can be changed by the composition, and it depends on the chemistry that you choose as well. So now you can change the ODT by changing N or the effective chi, and so now we have two norms that can independently affect domain size and temperature. So generally, domain sizes depend on the degree of polymerization and chi, and so these two can be changed independently by changing again degree of polymerization and composition. Right? So that's the reason we are interested in this. And so before we talk just about chi values in the Flory-Huggins parameter, we want to translate this to something that's more convenient to look at. That's the energy density. And so typically the Flory-Huggins parameter in experiments can be estimated from a variety of different ways. One way that you can do it is look at the solubility parameter, and the difference, the square of the difference in the solubility parameter is proportional to Flory-Huggins parameter. And then again, you have proportionality constants where you choose a reference monomer volume and scale it on the absolute energy from kinetic contribution from RT. And so this is a little non-standardized technique because the choice of VREF is not standardized, and it can be hard to compare across many different chemistries. And instead, if you just take X, or the energy density, it's a more convenient approach. And so here again, you basically lump together all the different constants, and then now you can study ratios of these energy densities. And again, you come with a reference-free description. And so x1 over x2 will be equal to TODT1 over TODT2. And so again, 1 and 2 can be similar systems that you can compare. And for example, 2 can be a pure block copolymer, and 1 can be the block random copolymer system that you want to study. And so now our goal really is, okay, so how do we get chi effective if I know the given composition and the interaction energy density for the pure block random copolymer? So again, really the goal of the study is to figure out what mixing rules apply and what are the limits of the applicability of these mixing rules. So in a lot of thermodynamics, a lot of mixing rules go with Berthelot mixing, which is you take the geometric mean of the interaction energies, and these do not apply for block copolymers because it always leads to mixing and not phase separation, right? And so there's other theories like regular mixing theory, and again, you can look at it based on the solubility parameter view or the monomer view, where you can say the chi, or the interaction energy density, is proportional to the net repulsion in the system, right? So again, if you look at the solubility parameter view, the net repulsion is just the square of the difference of the solubility parameters itself. And for the monomers, it's a little more complicated. It's epsilon AB, the repulsion strength between A and B, minus the repulsion strength in A and AB divided by 2. And so that works for a traditional block copolymer the way we sort of know it. And if you can extend this to block random copolymers, where now the second block here in purple is really going to be the solubility parameter can be obtained from group contribution. So it's delta for the random block would be Fa times delta A plus Fb times delta B. And so if you simplify that expression, you'll end up getting Fb squared times delta A minus delta B squared. And again, you can do the same thing for the monomer view, and you have to do a little bit of math, and the epsilon A to ARB is based on the probability of the contacts between each of these monomers. And so overall, you're going to get chi effective or x effective is equal to Fb squared times xab. So again, if it follows regular mixing theory, we will end up with this expression. And if that's not true, we might have to think about new theories for block random copolymer thermodynamics. And so some of the experimental studies that Brian's group has done previously shows that the regular mixing works for the case of styrene and isoprene. And the first challenge that they overcame was to get truly random copolymers without any gradients. And so by using this solvent mixture of cyclohexane and TEA, you're able to get very block random copolymers with no gradients or no tapers. And so you just get a single block, and then it switches to a random block. And so again, they were able to synthesize many different block random copolymers with different compositions and different degrees of polymerization. And so the ones highlighted in red showed that you can have two really different looking molecular weights with the same ODT. So now you can really decouple ODT from domain size by using this block random copolymers. Right, and then if you plot all of this data, interaction energy density versus composition, it seems to follow a quadratic scaling. And the study was done not just for styrene isoprene, but also their hydrogenated counterparts. So you have hydrogenated isoprene with styrene, and hydrogenated styrene is just vinyl cyclohexane. Okay, so it really worked for this binary type of block random copolymers where you have type A, and the second block was ARB. But when you tried a third block, this kind of scaling based on the solubility parameters did not seem to work. And so there was another equation that they developed. And so, the question then became, do we need new mixing rules, or how can we test the mixing rules? And so my group came in, and we decided to use a molecular model to ask the same question. So does regular mixing apply? Especially for the binary system, and can we look more at the molecular detail and try to learn something more about the system as to if it fails, why does it fail, etc. Okay, so we use a bead spring model for the block copolymers, and so each molecule has a different sequence. So using many different molecules really helps us go after this block random copolymers where every chain is really has a different sequence. Okay, and so these are freely jointed Feeney bonds. These model systems have been used to study block copolymers phase behavior, especially with the lamellar phase. And then we use n equals 60 beads per molecule. So the first block has 30 beads and the second block has 30 beads. And then the interactions between these beads are coming from the Weis-Chandra-Anderson potential. So these are purely repulsive. And we ran these simulations in NPT ensemble, and we chose epsilon AB. So for simplicity in this model, we chose epsilon AA and BB equal to 1. And so for repulsion, you want epsilon AB to be greater than 1, and you can drive phase separation if you have sufficiently high epsilon AB. And so in the cartoon, I've really shown A in red, B in blue, and in purple is actually type A, which is chemically identical. It's just shown colored differently in the other block, so you can sort of see that. And we implemented the simulations in labs. Okay, so our methodology for obtaining TODT is we used NPT simulations at various temperatures, and we changed composition. We used an initial lamellar configuration, and you find the melting temperature based on at the temperature at which the structure starts disintegrating. And we compute domain spacing, interfacial breadth. And then again, using all this data, because we have TODT data, we can then obtain the ratio for the TODT for the block random to the TODT of the pure block, and then we expect that to be following a scaling law. And if n equals 2, we would basically have regular mixing. Okay, so again, here is the example where delta epsilon AB was 2.5. We had n equals 60, and this is a fixed composition. So if I do simulations at different temperature, you can see at low temperature, we really have ordered structures. And at higher temperature, the structure becomes disordered. And we can examine the volume fraction profiles. And at lower volume fractions, you have high amplitudes. And then as you go towards disorder, you basically get much lower amplitudes. And so the structure disintegrates over time. And the simulation box gets more cubic. And so all of these are indicators that you're getting disordered structure. So we can also look at the domain spacing. And so if I add more A, or if I have lower FB, you can see that the domain size shrinks. And again, we can examine how the monomers are distributed. So, one hypothesis could be that if the monomers are not uniformly distributed, then, or there's some clustering within these domains, you would get deviations from regular mixing theory. And so when we just did visual inspection, it didn't seem like there was any clumping, and so we did not end up doing a clustering algorithm to further investigate this. So overall, domain sizes will shrink when more A is present in the random block, and it again looks like visually that most of these are distributed uniformly in the B domain. Okay, and then we can also go and look at our volume fraction data and obtain interfacial breadth. So the domain size is just the size of a unit cell, and the interfacial breadth we can obtain by just this approximation that the interface crosses at 50%, and you can see where it intersects the top and bottom lines, and then you can essentially get the domain thickness. And again, the domain thickness, as you add more A in the block copolymer, in the random block, the domain interfacial breadth really gets wider relative to domain size. And again, all of these are consistent that as you add more FB, the chi decreases and you're approaching more and more disorder. And so the structure resembles more disorder, progresses towards more and more disorder. Okay, and then finally we plotted the temperature scaling, so TODT versus over the pure block. And here the scaling follows FB proportional to the power is 2.39. It's close to 2, so regular mixing theory seems to be applying for the binary system of block random copolymers. And so I just want to conclude that for binary block random copolymers, the regular mixing theory predicts chi A to ARB is has this quadratic scaling with composition, and we did this in both simulations and experiments. And so we are also able to show that you can tune domain size and TODT independently, and then the regular mixing solution applies. And we can again investigate and look more deeply into measure quantitatively what the domain size is, what the interfacial breadth is, and how these change with composition. Right? And for ternary systems, I just want to sort of motivate future work. Again, if you use there's two different views again, right? So you can have the solubility parameter view or the monomer view, and these end up giving us slightly different equations and slightly different estimates. So in some experimental investigations, they found that the solubility parameter view does not seem to apply, and the monomer view seems to be what's followed in these systems. And so in the future work, the simulations will be used to also study the system. And that's the conclusions. Those are the conclusions for this work. I just want to also announce that our department at RIT has a new chemical engineering PhD program, and we are accepting PhD applicants for fall 2021. I'm going to leave you again with the conclusion slide. So it really looks like the monomer view might be a more general thermodynamic mixing view. And so I'm happy to answer questions. Thank you for attending my talk.